Lab 4 Oscillations. In this lab, we are given a mass oscillating on a spring. The video is then taken into Tracker and analyzed. Through code and GlowScript, we try to mimic the oscillation of the spring video and then compare the changes in different forms of energy that consist of kinetic, gravitational potential, spring potential, and the overall total change in energy. This lab focuses on the energy principle. Since the system is concluded of everything in the surroundings, no work is being done externally and all is done within the system. The energy transfers between kinetic and potential rather than outside work. Here in Tracker, we can see that the origin of access is set at the point where the start of the spring is, and that the spring extends towards a meters of 0.7 when the mass is on it, and oscillates in the horizontal direction and in the vertical direction. In order to calculate missing information, we are given the mass of 0.402 kilograms and the stretch distance of the spring of 0.7 meters. We know that there's a gravitational force acting on it, which is mass times gravity, and a spring force acting on it, which is the spring constant times the change in the distance of the spring. From Tracker, we are getting the period time for one oscillation of 1.425 seconds. And using the fundamental principles of Newton's second laws, we use to calculate the spring constant and L naught, which is the resting length of the spring. So, a time period equals 2 pi square root m over the spring constant. So a spring constant would equal 4 pi squared times mass divided by the period of oscillation, which gives us a spring constant of 11.13. We also know that since net force equals 0, we can set that the gravitational force equal to the spring force and find the change in S or through that, and then get the resting length of the spring to be 0.346 meters. In the code, we input the mass in the video and the initial position from Tracker. And then we input the G constant, which is 9.8, and the spring constant and L naught calculated previously in inputting the energy formulas, which consist of kinetic energy, which equals 1/2 times the ball's mass times the ball's velocity squared, gravitational potential, which equals the ball's mass times the G constant times the change in height, and the spring potential energy, which is 1/2 times the spring constant times the change in the spring squared, and total is all of them added together. Setting initial, in this part of the code, we set the initial energies to the previously found, and then the net force is the gravitational and spring force added together. Using Newton's second law to update position and velocity, where ball's final velocity equals ball's initial velocity plus F net over the ball's mass times delta t, and ball's final position equals ball's initial position plus ball's velocity times delta t. And then we update the spring length using the same formulas, and we find the change in energies through subtracting from the final from the initial. In the code output, we can see that the different y position graph, which shows that there is human error due to the fact that the code creates a perfect situation in Tracker. There is human error because of the difficulty of tracking the ball through Tracker. So those are off due to human error. And then here we can see that the red is the change in gravitational potential, the green is the change in spring potential, the blue is the change in kinetic energy, and orange is the change in total energy. We can see that the change in energy is 0, so no work is being done, and the gravitational and spring potential act in opposites of each other. The energy principle is satisfied in the outputs. Gravitational potential and spring potential are oscillating in the same time period but in opposites, so spring potential increases, gravitational potential decreases. Kinetic energy increases and decreases as gravitational and spring potential increase and decrease. The change in energy of the system is 0 because no energy is being transmitted from the system to the surroundings because all the forces are included in the system. The graphs are not perfect because they account for human error in Tracker. The time period for x equals 1.614 seconds. The time period for y equals 1.425 seconds. Although they are close and similar, they are not the same. The time periods are not the same because they account for the different oscillations. The time period for x accounts for the spring's horizontal oscillations, while the time period for y accounts for the spring's vertical oscillation. They are different because they account for different things. Overall, in this lab, we focus on the energy principle when energy transfers within the system. Since the system includes all of the surroundings, no work is being done externally, so change in energy is always zero. The energy transfers from kinetic to gravitational potential and spring potential.